Welcome, everyone, to another episode of Energy Talks. Today, we have a fascinating topic, the oxygen evolution electrocatalysis on oxide surfaces.
Hey Joanna, thanks for having me. I'm excited to dive into this. You know, the idea of scaling relations in electrocatalysis is pretty revolutionary.
Absolutely, Matthew. It's like discovering a universal grading system for catalysts. Imagine if each school could use the same scale to evaluate students, no matter their curriculum.
That's a neat way to put it. So, what exactly does this universality and scaling relations mean for clean energy?
Great question, Justin. It means we've found a universal pattern in how different catalysts behave for the oxygen evolution reaction, something crucial for generating clean energy through electrochemical water splitting.
It's like knowing that no matter what stove you use, you'll melt chocolate at the same temperature. Universality helps predict how different materials will perform in generating oxygen.
And the big focus here is on adsorption energies of intermediate particles like OH and OOH, which correlate linearly.
So, this graph, the activity volcano plot, right? Basically maps catalyst activities based on their surface binding strengths?
Exactly. The volcano plot shows the relationship between power performance and binding energy, guiding researchers in finding the best catalysts.
So, Matthew, why is this important? Why focus so much on these adsorption energies?
Well, Joanna, it's these adsorption energies that determine the efficiency of the oxygen evolving reaction. Without efficient catalysts, this process requires more energy, making it costlier.
What's fascinating is how the energy needs of these reactions are independent of the pH or potential values. It's universal for the oxygen evolving reaction. Imagine simplifying such evaluations.
That's like having one set of rules that apply to your math tests everywhere, no matter who's grading.
Exactly, Justin. It's a universal descriptor or a common marker that makes evaluating new materials easier and speeds up discovering efficient catalysts.
But here's the twist, while this single descriptor simplifies things, could it be too simplistic? Are we overlooking other factors like durability?
That's a significant point, Matthew. Sometimes, focusing too narrowly could miss other crucial factors like long-term stability or environmental robustness.
Kind of like buying the fastest car but not checking if it's suitable for winter driving. Fast but not practical for all conditions.
True, Justin. Theoretical insights need experimental backing to be practical, don't they?
Yes, absolutely. Experimental validation is key. Like our cooking analogy, the recipe might look perfect, but the actual taste can vary.
That's where combining theoretical predictions with real-world experimentation becomes essential. It's about bridging that gap.
So, what's the next step in improving these catalysts? How do we make them better?
That's an intriguing question. The study suggests stabilizing the O-H intermediate might be the key to better catalysts.
So, perhaps we need to think outside the box, bring in new ideas, like borrowing from nature and using innovative materials.
Yes, interdisciplinary approaches like biomimicry, imitating natural processes, might provide new pathways for innovative solutions.
It's like borrowing design elements from nature's most effective systems and applying them to our technology.
As we conclude, let's recap the main insights. Discovering universal scaling relations helps us understand better, create efficient catalysts, and perhaps redefine clean energy processes.
And by focusing on a universal descriptor, although useful, we must remember to consider factors like stability and practical application.
Indeed, collaboration and creativity are vital, bridging theory with practice to achieve sustainable breakthroughs.
So, tune in next time for more deep dives into the science that's changing our world. Thanks for listening.